Students, today's topic is P block elements. Group number 15, group number 16, group number 17 and group number 18. Now, first about group number 15, it's called as nitrogen family. The elements belongs to group number 15, nitrogen. Atomic number of nitrogen is 7. Next element is phosphorus. Atomic number is 15. Next one, arsenic. Atomic number is 33. After arsenic, Sb. Atomic number is 51. Next is bismuth. Bismuth. So atomic number of bismuth is 83. 83. Now, so about the electronic configuration with respect to nearest noble gas. For nitrogen, nearest noble gas is helium, 2s2, 2p, 3. 1s2, 2s2, 2p3. Helium 1s2. For phosphorus, nearest noble gas is neon, 3s2, 3p3. Okay. Arsenic, nearest noble gas is argon, 18, 3d10, 4s2, 4p3. Okay. Here noble gas, nearest noble gas is krypton, 4d10, 5s2, 5p3. Next one, xenon, 4f14, 5d10, 6s2 and 6p3. Okay. So this is about electronic configuration of nitrogen family. Now, so about the properties of nitrogen family properties. Now, so about the physical state. First about physical state. So nitrogen exists as diatomic molecule, whereas other elements belongs to group number 15. They are tetraatomic and their geometry is tetrahedral, tetraatomic. Now, and other properties of group number 15. First about atomic radii, atomic radii. So down the group increases because electrons are added to the new principal shell. Therefore, atomic radii increases down the group. Okay. Next about ionization enthalpy or ionization potential. Ionization enthalpy. So down the group, ionization enthalpy decreases. Okay. Decreases down the group because atomic size increases. Therefore, ionization enthalpy decreases down the group. Okay. Next about electropositive character and metallic character. Electropositive and metallic character. Metallic character. So down the group, electropositive character increases as well as the metallic character increases. Therefore, the first two elements, nitrogen and phosphorus, these two are non-metals. Non-metals. Okay. Next, antimony and the arsenic. These two are metalloids. Metalloids. Last one, bismuth is a metal. Bismuth is a metal. Okay. So this is about electropositive character as well as metallic character. Now, it's about catenation property. Catenation. Tendency to exhibit catenation is less. But among the group number 15, okay, nitrogen and phosphorus, it exhibit catenation. Simple example for catenation property of nitrogen. Hydrazine molecule NH2 NH2, hydrazine. There two nitrogen atoms, they link together. Next one is hydrozoic acid, HN3, hydrozoic acid. Okay. So this is about catenation property of group number 15 now. Next about allotropic forms, allotropy. Except beryllium, except bismuth, all other elements exhibit allotropic form. Phosphorus, it exhibits 5 allotropic forms like white phosphorus, or it's also called as yellow phosphorus, most reactive, very reactive, red phosphorus, black phosphorus, scarlet phosphorus, and violet phosphorus. So these are the 5 allotropic forms of phosphorus. So next property of group number 15 element is oxidation state. Okay. Oxidation state. So common oxidation state +3 and +5. +3 and +5. Okay. So down the group, stability of +5 oxidation state decreases. That is due to inert pair effect. Now, so nitrogen and phosphorus exhibit -3 oxidation state in their hydrides. Here nitrogen, it exhibits the variable oxidation state. It varies from -3 to +5, So oxidation state of nitrogen -3 to +5, Now, some of the example for -3 oxidation state, ammonia, NH3, where nitrogen exhibit -3 oxidation state. Now, the next compound is hydrazine, NH2. Oxidation state of nitrogen is -2. Hydroxylamine, NH2OH, here oxidation state is -1. Nitrogen molecule, when you consider, this is 0. Now, about the +1 oxidation state, +1. N2O, nitrous oxide, +1. Nitric oxide, here, +2. Then dinitrogen trioxide, +3. Dinitrogen tetroxide, +4. Dinitrogen pentoxide, N2O5, +5. Okay. This is about oxidation state of nitrogen, and is one of the anomalous property of nitrogen. Now, next about the covalency. So maximum covalency of nitrogen, it exhibits 4. That due to the absence of vacant d orbital. But other element belongs to group number 15. It exhibits the covalency 5 or 6. For example, phosphorus, it exhibits 5. And in this compound, PCl5. No. PF6 minus, here it exhibits covalency, maximum covalency 6. Now, so this is about the covalency. Now, other property, where nitrogen forms p-pi multiple bond, whereas other element, they form p-pi d-pi bonds. Nitrogen, it forms p-pi multiple bonds, and other elements of the same group, it forms p-pi d-pi multiple bonds with oxygen. Now, so other properties. Next, we'll move on to chemical properties of nitrogen family, So nitrogen is inert. Okay. Why nitrogen is inert? Okay. That is due to the bond dissociation energy. And among these 15th group element, phosphorus is most reactive element. Now, so down the group, when you consider from nitrogen to bismuth, the reactivity decreases down the group. Okay. Next, reaction with hydrogen. Okay. Elements of group number 15 reacts with hydrogen and they form hydrides of the type MH3. Reaction with hydrogen. They form hydrides, hydrides of the type MH3. Now, for example, hydride of nitrogen is called as ammonia, NH3. You can write NH3. Now, hydride of phosphorus, phosphine. Hydride of arsenic, arsine. Hydride of antimony is called as stibine. Okay. Hydride of bismuth is called as bismuthine. See. These are hydrides of elements of group number 15. Now, so about the properties of hydrides are very, very important. Now, so down the group, bond length. Between nitrogen and hydrogen increases, bond length increases. Okay. When bond length increases, bond angle decreases. Bond angle decreases down the group. Now, so about the thermal stability. Okay. Down the group, thermal stability decreases. Now, so about the basic nature. Down the group, basic nature decreases. So, elements of group number 15 with hydrogen, they act as a Lewis base. So, down the group, basic nature decreases. Down the group. Ammonia exhibit highest basic nature. So, this is about the properties of hydrides of group number 15. Now, it's about the melting point and boiling point. Ammonia has high boiling point due to intermolecular hydrogen bonding. It can form hydrogen bond. And type of hydrogen bonding is intermolecular hydrogen bonding. Therefore, the boiling point of ammonia is highest. Now, so boiling point decreases from phosphine to bismuthine. Boiling point decreases from phosphine to bismuthine. Now, next about solubility. So, solubility property. So, ammonia is highly soluble. Again, that is due to the formation of hydrogen bond. Now, ammonia is highly soluble due to hydrogen bonding. Now, solubility of hydrides decreases down the group. Okay. Now, so this is about reaction with hydrogen and very, very important concept. And almost if you go for all the groups, when they react with hydrogen, they form hydrides. And these properties, the variation of property, it remains almost same for all the groups. Now, next, reaction with halogen. Okay. So, elements of group number 15, when they react with halogen, they form two types of halides. Okay. EX3 or EX5. Reaction with halogens. It forms halide of the type EX3 or EX5. EX3 or EX5. Now, trihalides. For example, NCl3, PCl3. Okay. Trihalides of the group number 15. Okay. And these trihalides, they act as a Lewis base. And Lewis base character decreases down the group. Lewis base character decreases down the group. That is due to the decrease in electronegativity. Down the group, electronegativity decreases. As a result, Lewis base characteristic also decreases. Now, it's about EX5. Nitrogen fails to form of the type pentahalide. Phosphorus forms pentahalide, PCl5. Okay. Why nitrogen fails to form pentahalide? That is due to smaller size and also due to the absence of vacant d orbital. It fails to form pentahalide. Now, so this is about the reaction with halide. And except NF3, all other halides, it undergo hydrolysis. Now, the tendency of hydrolysis decreases down the group. Now, when you compare PCl3, ACl3 and NCl3, down the group tendency of hydrolysis decreases. Now, when you compare hydrolysis of NCl3, PCl3, ACl3, so down the group hydrolysis decreases, tendency to undergo hydrolysis decreases. Now, NCl3, when it undergo hydrolysis, it gives ammonia, NH3, and other product is hypochlorous acid, HClO. Similarly, PCl3 undergo hydrolysis to give H3PO3, orthophosphorus acid, and HCl. Then ASCl3, trihalide of arsenic, when it undergo hydrolysis, that gives H3ASO3 and HCl. So this is about hydrolysis of trihalides. Now, when you compare trihalides and pentahalides, trihalides are more stable compared to pentahalides. Now, so pentahalides also undergo hydrolysis. One important reaction is PCl5. When PCl5 is subjected to hydrolysis, it gives H3PO4 and other byproduct is HCl. Now, say about the type of hybridization. PCl5, it undergo which kind of hybridization? sp3 dehybridization. And geometry of PCl5 is trigonal bipyramidal. Now, so all pentahalides except nitrogen, they act as a Lewis base. That is due to the presence of vacant d orbital. So pentahalides of nitrogen family, it acts as a Lewis base. That is due to the presence of d orbital. Now, so in the pentahalides, if you consider MX5, that reacts with halide ion, that gives MX6 minus. Now, here during this process, hybridized state changes. Now, this is sp3d, and after the formation of this compound, it becomes the hybridized state sp3d2. So sp3d2 geometry changes. Geometry means geometry from trigonal bipyramidal to octahedral. So this is about halides. Next we will move on to reaction with oxygen. When elements of group number 15, they react with oxygen, they form different types of oxygen. Oxygen of the type M2O3 and M2O5. Trioxides of nitrogen, phosphorus and arsenic are acidic in nature. Okay. When you compare N2O3, P2O3 and arsenic, AS2O3, they are acidic in nature. Now, but acidic nature decreases down the group. That is due to decrease in electronegativity. Now, so among these N2O3, the acidic strength is highest for N2O3, least is for AS2O3. So down the group electronegativity decreases. Now, say about Oxide of antimony, it is amphoteric. Okay. Oxide of bismuth, it is basic. Metallic oxide, it is basic. Okay. Now this is about trioxide. Now it's about the pentoxide. So all pentoxides are soluble in water and they form acids. That means they are acidic in nature. Now, for example, if you consider N2O5, nitrogen pentoxide, N2O5, phosphorus pentoxide, pentoxide of phosphorus, similarly pentoxide of arsenic, pentoxide of antimony, and pentoxide of bismuth, Now, here which is most basic? So acidic strength increases, here acidic strength decreases down the group, as the electronegativity decreases. Now, one more, when you consider oxide of the same element, as the oxidation state increases, where acidic nature increases. Now we can take the example of oxide of nitrogen, +1 to +5, N2O, NO, okay, then NO2, N2O3, and N2O5. Here, this is +1, +2, yeah, N2O3, we'll take N2O3. This is +3, +4, and +5. Now, so these oxides, as the oxidation state increases, acidic strength also increases. Okay. Now, when you consider NO2, nitrogen dioxide, NO2. NO2 contains odd electron. Therefore, NO2 undergo dimerization to give N2O4. So, between this N2O4 is more stable. Now, when you go for magnetic property, NO2 is paramagnetic due to the availability of odd electron, and that odd electron is involved in the bonding during the formation of N2O4, Therefore, here there is no odd electron, so magnetic property is diamagnetic. So paramagnetic is converted into diamagnetic. So this is about oxides of nitrogen family. Next about Oxo acids of nitrogen, Oxo acids of nitrogen. Simple example for oxo acids: nitrous acid, nitric acid. So nitrous acid formula HNO2. Nitric acid, the formula is HNO3. Now, hyponitrous acid. So formula of hyponitrous acid is H2N2O2. Now, next one is pernitric acid. The formula of pernitric acid is HNO4. Now, so these are example for oxo acids of nitrogen. Now, next about strength and stability of oxo acids. Strength of stability of oxo acids with same oxidation state decreases rapidly down the group. That is due to decrease in electronegativity of the central atom. Now, when you consider oxo acids, examples like this: HNO2, HNO3 will take, then H3PO4, then H3ASO4, then H3BiO4. Now, here oxidation state of central atom is same, that is +5. Okay. So in this case, the stability that depends on the electronegativity. So down the group, electronegativity decreases, strength as well as stability decreases when the oxo acids are having same oxidation state. So here this is the most stable. The least stable is, because since oxidation state is same, so it depends on the electronegativity. Okay. So next one about the anomalous properties of nitrogen. So nitrogen exhibit variable oxidation state. It fails to form NCl3. Why nitrogen exhibit anomalous property? The reason is due to small size and due to the absence of vacant d orbital, high electronegativity, and also due to high ionization enthalpy. It exhibits anomalous property. Now, next we will move on to the compounds of nitrogen. Okay. The first compound of nitrogen is dinitrogen, N2, dinitrogen, N2. Now, it's about the preparation of dinitrogen. Ammonium nitrite, NH4NO2. On heating, it decomposes to give nitrogen and H2O, nitrogen and H2O. Similarly, one more compound, ammonium dichromate, NH4 twice, Cr2O7. On heating, it decomposes to liberate nitrogen and chromic oxide, Cr2O3 plus H2O. These are simple methods of preparation of nitrogen. Very pure nitrogen is obtained by heating barium azide or sodium azide. Okay. Now, it's about the preparation of very pure nitrogen. Barium azide, BaN3. On heating, okay, that decomposes to give barium, liberating nitrogen. The obtained nitrogen is very pure. Okay. This is about the preparation of pure nitrogen. Now, it's about the chemical properties of nitrogen. Now, nitrogen, when reacts with lithium or magnesium or aluminium, they form respective nitride. So lithium forms lithium nitride. Magnesium forms magnesium nitride. Aluminium forms aluminium nitride. Now, here lithium nitride is ionic. Is an example for ionic. Aluminium nitride is an example for interstitial nitride. So other chemical properties. Nitrogen reacts with hydrogen, that forms ammonia. Same thing we'll discuss under manufacture of ammonia. Okay. Then one more reaction with calcium carbide. Okay. It gives nitrolium, CaCN2. And see, this compound is called nitrolium. This is about the chemical properties of nitrogen. Now, next about ammonia. In ammonia, about the manufacture of ammonia by Haber's process. So nitrogen reacts with hydrogen, okay, in the presence of iron as a catalyst at 200 atmospheric pressure, around 673 Kelvin, that gives ammonia. And this reaction is exothermic and it is reversible reaction. It is about Haber's process in the manufacture of ammonia. Now, it's about the after obtaining gas, it is dried by treating with calcium oxide, not with other drying agent. When you take sulphuric acid, ammonia reacts with sulphuric acid to give salt. Therefore, it is treated with calcium oxide. So ammonia is dried by treating with calcium oxide. Now, next about the properties of ammonia. Properties of ammonia. Ammonia is basic in nature due to the presence of lone pair of electron on the nitrogen atom. So basic nature of ammonia, okay, confirmed by treating with acid like HCl or sulphuric acid. We'll write like this. First about the on treating with water. So ammonia is an example for Lewis base. Here the water donates proton. This becomes NH4 plus and OH minus, NH4 plus and OH minus. This is a reversible reaction. Next one, reaction with hydrochloric acid. When ammonia reacts with hydrochloric acid, that forms ammonium chloride. When ammonia reacts with sulphuric acid, it forms ammonium sulfate as a salt. So these two reactions confirms the basic nature of ammonia. Now, other chemical properties of ammonia. Look here. Now, when ammonia that reacts with sodium, that forms sodamide, NaNH2, liberating hydrogen. Sodamide is formed. Now, reaction with copper oxide. Now, so when ammonia reacts with the copper oxide, from this hydrogen is removed. Okay. Nitrogen gas is liberated and other compounds are copper and H2O. Now, similarly, reaction with oxygen in presence of platinum, that gives nitric oxide, NO. Then other reactions with the chlorine. Now, here it depends on the reaction condition, chlorine. Now, if excess of ammonia is taken, excess of ammonia. When excess of ammonia reacts with the chlorine, that gives ammonium chloride, NH4Cl, liberating nitrogen. Now, if excess of chlorine is taken, that gives NCl3, and other compound is HCl. Okay. Similarly, ammonia on treating with silver chloride, AgCl, in basic medium, NaOH, basic medium, that forms a complex compound. Ag, NH3 twice and Cl. Similarly, an ammonia is treated with copper sulfate, that gives in alkaline medium, that forms a complex compound. Okay. So this is about the chemical property of ammonia. Next about nitric acid. About the manufacture of nitric acid by Oswald's process using ammonia. Okay. When ammonia is subjected to oxidation in presence of platinum, that gives nitric oxide. Then nitric oxide is subjected to oxidation in presence of catalyst, that gives NO2, nitrogen dioxide. Nitrogen dioxide is treated with water, that gives nitric acid. So this is about the manufacture of nitric acid. Now, we'll move on to properties of nitric acid. Nitric acid is an example for monobasic acid. Basicity is 1. Now, about oxidizing property of nitric acid. So nitric acid, it oxidizes carbon to carbon dioxide. About the oxidizing property. It oxidizes carbon to carbon dioxide. Then on treating with iodine, iodine, it forms HiO3, hydroiodic acid, liberating nitrogen dioxide, NO2. Now, Next, reaction with more electropositive metals, So this depends on the reaction condition. When nitric acid reacts with zinc, When reacts with nitric acid, Cold and dilute nitric acid, It gives zinc nitrate, Zn, NO3, twice zinc nitrate. And byproduct is ammonium nitrate, NH4NO3 and water. Similarly, zinc reacts with hot and dilute nitric acid. The major compound is same, that is zinc nitrate. Zinc nitrate is formed, ZnNO3 twice, liberating nitrous oxide, laughing gas, nitrous oxide. Another compound is water. One more reaction, when zinc reacts with hot and concentrated nitric acid. It gives zinc nitrate, ZnNO3 twice, zinc nitrate, liberating nitrogen dioxide and water. Okay. So this is about oxidizing property of nitric acid. Similarly, nitric acid reacts with less electropositive metal like copper. Copper on treating with nitric acid, that gives bluish green solution of cupric nitrate, liberating reddish brown fumes of nitrogen dioxide. Now, reactive metals on treating with concentrated nitric acid, it loses its chemical property, that's called as passivity. For example, aluminium on treating with nitric acid, a thin coating of aluminium oxide is formed and it acts as a protective layer. Therefore, aluminium loses its chemical reactivity, that's called as passivity. So due to this reason, the nitric acid is transported using aluminium container. Next one about the phosphorus. So compound of phosphorus, first one is phosphine, pH 3, phosphine. The preparation of phosphine, when white phosphorus, this reacts with sodium hydroxide solution. That gives sodium hypophosphite, liberating phosphine, pH 3. Sodium hypophosphite is formed, liberating phosphine. Now, similarly, there is one more reaction where phosphine is prepared by treating calcium phosphide. Calcium phosphide is subjected to hydrolysis. So on treating with water, it gives calcium hydroxide, CaOH twice, calcium hydroxide, liberating phosphine. Now, say about PCl3. PCl3 is an example for sp3 dehybridization. sp3 dehybridization. sp3 dehybridization. What is shape of PCl3? T shape. Now, when PCl is subject to hydrolysis, that gives H3PO3. Now, PCl5, compound of phosphorus, PCl5. PCl5, it exhibits sp3d2. Now, what about geometry of PCl5? Trigonal bipyramidal. So these are the compounds of phosphorus. And about some important oxide of phosphorus, P4O6 and P4O10, phosphorus trioxide and phosphorus pentoxide. Now, we can write like this, P4O6. Now, look at the structure of P4O6. Now, there are 4 phosphorus Each phosphorus is linked by oxygen. Each phosphorus is linked by oxygen. P4O6. Similarly, P4O10, P4O10, P4O10. Now, in the structure of P4O10, phosphorus, 4 phosphorus, and in each phosphorus, it contains double bonded oxygen, double bond with the oxygen atom. P4O10. Okay. So these are the important compounds of phosphorus, Now, about oxo acids of phosphorus, there are different series of oxo acid, phosphorus series and phosphoric series, phosphorus acid series and phosphoric acid series. Now, first about phosphorus acid series. Phosphorus acid series. So, example for phosphorus acid series. The first compound is hypophosphorus acid. Hypophosphorus acid. Hypophosphorus acid. The formula of hypophosphorus acid is H3PO2. Now, it is also called as phosphinic acid. Phosphinic acid. Now, the next one, orthophosphorus acid. Orthophosphorus acid. Orthophosphorus acid. Now, the formula of orthophosphorus acid H3PO3. Now, it is called as phosphonic acid. Phosphonic acid. Now, one more, hypophosphorus acid. Hypophosphorus acid is given, that is H3PO2. Now, pyrophosphorus acid. Pyrophosphorus acid. Now, the formula of pyrophosphorus acid is H4P2O5. So all these comes under phosphorus acid series. Now, next series is called phosphoric acid series. Here you should know the structure, then about their oxidation state. Here, what about oxidation state of this phosphorus? It is +3, here -4, this is +1. And oxidation state of this phosphorus, +3, this is -6, this is +3. Phosphorus +3. In this case, here this is 10. Okay. Now you have to go for the oxidation state of phosphorus. And basicity or basicity of phosphoric acid, that depends on the number of OH group. If there is one OH group, basicity is 1. If there is two OH group, basicity is 2. Now, next about phosphoric acid series. In this first compound is phosphoric acid. Or it is also called as orthophosphoric acid. H3PO4. It is an example for tribasic. Oxidation state of phosphorus is 5. Okay. Next, orthophosphoric acid. Orthophosphoric acid. Now, what is the formula for orthophosphoric acid? Okay. H4P2O6. Orthophosphoric acid. Yeah. Phosphoric acid nothing but orthophosphoric acid, that is H3PO4. Now, next about hypophosphoric acid. Hypophosphoric acid. Now, the formula of hypophosphoric acid is H4P2O6. H4P2O6. Next one is pyrophosphoric acid. That is H4P2O7. Okay. This series is called as phosphoric acid series. Now, Next, we'll move on to oxygen family. Oxygen family. It is also called as group number 16. Group number 16. Oxygen family. Now, oxygen family. First element is oxygen. Okay. Then comes sulfur, selenium, tellurium. Last one is polonium. About the atomic number of oxygen is 8. 8. Sulfur is 16. Now, selenium is 34. 34. This is 52. And next one is 84. 84. Now, so electronic configuration. Nearest noble gas is helium. 2s2. 2p. See, 1s2. 1s2. Then 2s2. 2p. 4. 6 plus 2, 8. Neon. Neon. 3s2. 3p4. Next one is argon. 4s2. 4p4. 4p4. Next about krypton. Krypton. 3d10. 3d10. Sorry. 3d10. 4s2. Yeah. This is 4d10. 4d10. 5s2. 5s2. 5p4. 5p4. Last one is xenon. 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 Atomic number xenon is 54. 4f 14. 5d10. 6s2 and 6p4. 54 plus 14 68 plus 10 78 80 84. 84. This is about electronic configuration. Now, it's about the general trend in the properties. Atomic size increases down the group. Ionization enthalpy decreases down the group. Electropositive character and metallic character increases down the group. Therefore, here, oxygen and sulfur, these two are non-metals. Selenium and tellurium, they are metalloids. But last one is radioactive metal. Polonium is radioactive metal. Now, atomic size increases down the group because the newly added electron goes to new principal shell. Therefore, down the group, atomic size increases. Atomic size increases. Now, about electron gain enthalpy. Down the group, electron gain enthalpy decreases. But there is one exceptional cases. Elements of second period and elements of third period. Here, this is element of second period. This is element of third period. Sulfur has got more electron gain enthalpy than the oxygen. Sulfur has got more electron gain enthalpy than the oxygen. Electron gain enthalpy of oxygen is less than the sulfur. That is due to smaller size of oxygen. So, electron gain enthalpy of sulfur is more than the oxygen. So, electronegativity. Electronegativity decreases down the group. Now, about nature of bonding. Nature of bonding. Nature of bonding. First, we will consider the oxygen element. So, what about oxygen? Oxygen forms ionic bonds with more electropositive metal. And it forms covalent bond with less electropositive metal. So, covalent bond is observed when it combines with less electropositive metal or non-metals. Non-metals. Okay. Next, other elements like sulfur, selenium, tellurium, they form covalent bond. So when oxygen reacts with more electropositive metal, they form ionic bond, and with non-metal, it forms covalent bond. All other elements, sulfur, selenium, tellurium, they form covalent bond. So this is about nature of bonding. Now, next about allotropy. So all the members exhibit allotropy, but tendency to exhibit allotropy decreases down the group. So oxygen exhibit allotropy form like dioxygen and ozone, O3. Sulfur exhibit monoclinic sulfur, rhombic sulfur, plastic sulfur, then amorphous sulfur. These are the different allotropic forms of sulfur. Now, about catenation. So oxygen and sulfur, it exhibit catenation. But sulfur has got greater tendency for catenation after carbon. So this is about catenation property. Now, it's about the chemical property, Now, the reaction with hydrogen, chemical properties. So elements belongs to group number 16 when they react with hydrogen, they form hydride of the type, okay, H2E or H2M. Now, first one is H2O, water, H2S, hydride of selenium, hydride of tellurium. Now, the property of hydrides is almost similar to hydrides of group number 15. Down the group, bond length increases, bond angle decreases, thermal stability decreases down the group, reducing property increases down the group, So these are the properties of hydrides, Now, next about the reaction with halogen, When elements of group number 16 reacts with the halogen, they form different types of halides, Now, halides of oxygens are not very stable. For example, oxygen difluoride, OF2, then Cl2O7, I2O5. These are halides of oxygen, but they are not stable. Same reaction with the oxygen. Other than oxygen, rest of the elements, when they react with oxygen, they form different types of oxides. Oxides of the type common oxides MO2 and MO3. Now, like sulfur dioxide, SO2, sulfur trioxide. Similar, selenium oxide. Now, here the reaction of oxygen with other metal, they form different types of oxide. Now, acidic oxide, first one about acidic oxides. When oxygen reacts with non-metals, they form acidic oxide, like CO2, SiO2, N2O5, then SO2, Mn2O7. All these are example for acidic oxide because when they treated with water, they form acid. Similarly, basic oxide. When oxygen reacts with metals, especially group number 1 and group number 2, they form basic oxide. Now, example for basic oxide, Na2O, calcium oxide, PbO, etc. Okay. They form basic oxide. Next about amphoteric oxide. So example for amphoteric oxide, which acts as the acid as well as the base, amphoteric oxide. Some of the example for amphoteric oxide, PbO2, ZnO, alumina, Al2O3. These are example for amphoteric. Neutral oxide. So example for neutral oxide, carbon monoxide, NO, N2O. These are example for neutral oxide, or water. Example for neutral oxide. So these are the different types of oxide. Similarly, mixed oxide. Simple example for mixed oxide, oxide of lead, PbO4. So it is a combination of PbO and PbO2. See. is an example for mixed oxide, an example for mixed oxide. Now, say about thermal stability. Thermal stability. When you consider oxides of the elements belongs to group number 16 other than oxygen, like sulfur, SO2, tellurium, selenium, then about the polonium. Now, we will consider these three. Now, sulfur dioxide thermally more stable. The least stable is here selenium oxide. Now, next about compounds of oxygen, dioxygen, O2. O2 is prepared when potassium chlorate on heating. When potassium KClO3 on strong heating, that decomposes to give KCl, liberating oxygen, O2. Potassium chlorate on heating, that gives potassium chloride, liberating oxygen. See. Now. Or mercuric oxide on heating, HgO on heating, that gives mercury, liberating oxygen. So these are the simple method in the preparation of or we can go for electrolysis of water. Now, about the properties of oxygen. So oxygen reacts with sodium, that gives sodium oxide. Okay. Oxygen reacts with iron, that gives ferric oxide. On treating with iron, that gives Fe2O3. Then reaction with phosphorus, that gives phosphorus pentoxide, P4O5. Then reaction with carbon disulfide. Here carbon disulfide dissociate to give carbon dioxide and sulfur dioxide. Similarly, one example for combustion process, methane on heating with oxygen, that gives carbon dioxide and water. Now, say another compound of oxygen is ozone, O3. Now, say about the preparation of ozone, where oxygen is subjected to silent electric discharge in a discharge tube, where oxygen is converted into ozone. Now, the reaction is endothermic reaction, heat is absorbed. Therefore, reaction is carried out in silent electric discharge. Otherwise, oxygen further it decomposes to give oxygen. Now, 3O2. Electric discharge is carried out in a silent electric discharge, that gives ozone, 2O3. Delta H is positive. The reaction is endothermic. Now, so about the properties of ozone. Chemical properties. When it reacts with nitric oxide, ozone reacts with nitric oxide, that gives NO2 and O2. Then reaction with hydrogen sulfide, H2S, hydrogen sulfide. When ozone reacts with H2S, that gives sulphuric acid, H2SO4. Similarly, on treating with lead sulfide, PBS, black colored lead sulfide is converted into a white precipitate of lead sulfate. Then, about the ozonolysis, ozone reacts with unsaturated compound, alkenes or alkynes, then followed by hydrolysis. Now we'll go for ethene, simple compound, ozonolysis. That gives 2 moles of formaldehyde. Hydrolysis is carried out in presence of zinc. So one more reaction, the reaction with HCl and stannous chloride, where ozone oxidizes stannous chloride to stannic chloride, SnCl4. So these are some important chemical properties of ozone. Next, moving on to sulfur dioxide, SO2. Sulfur dioxide is prepared Preparation of sulfur dioxide. Direct combustion of sulfur. Sulfur undergo combustion, that gives sulfur dioxide. Now, in the laboratory, sulfur dioxide is prepared by treating copper with sulphuric acid, concentrated sulphuric acid. That forms copper sulfate, liberating sulfur dioxide, This is about lab preparation of sulfur dioxide. Now, it's about the properties of sulfur dioxide. Sulfur dioxide acts as a reducing agent. It acts as a reducing agent. Properties. It acts as a reducing agent. Yeah. When sulfur dioxide, SO2, reacts with chlorine in presence of water, it reduces chlorine to HCl. Another byproduct is sulphuric acid. It reduces chlorine by itself undergoing oxidation. So, sulfur dioxide oxidizes to give sulphuric acid. Now, similarly, it decolorizes potassium permanganate solution. When sulfur dioxide gas is passed through pink solution of potassium permanganate, pink color is discharged. Okay. These two are simple example for reducing property of sulfur dioxide. Next, about oxidizing property. It acts as a oxidizing agent. Now, when sulfur dioxide reacts with it reacts with hydrogen sulfide, H2S, hydrogen sulfide. It oxidizes hydrogen sulfide to give sulfur, and byproduct is water. Or it oxidizes acidified ferrous sulfate to ferric sulfate, or on treating with potassium permanganate. Okay. It converts potassium permanganate to MnSO4. So, here sulfur dioxide, it acts as a oxidizing agent. Now, next, about bleaching property of sulfur dioxide. So, bleaching property of sulfur dioxide is due to reduction. When sulfur dioxide reacts with moisture, that provides nascent hydrogen. Thus obtained nascent hydrogen decolorizes organic matter. And here, bleaching property of sulfur dioxide temporary. The bleached article once again is exposed to air, that regain its original color. In order to bleach hair, then feather or ivory, sulfur dioxide is taken. Now, next, about sulphuric acid, H2SO4. It's about the manufacture of sulphuric acid by contact process. It involves different steps. Okay. Manufacture of sulphuric. First one, about the production of sulfur dioxide, where iron pyrite or sulfur is burnt in a pyrite burner that produces sulfur dioxide. Then sulfur dioxide is subject to oxidation to give sulfur trioxide. Then that sulfur trioxide is absorbed in 98% of sulphuric acid to give oleum. Fuming sulphuric acid. To the fuming sulphuric acid, on adding calculated amount of water, that gives sulphuric acid. Sulphuric acid is an example for dibasic acid. There are two replaceable hydrogen atoms. It acts as a very good dehydrating agent. Now, about the dehydrating property of sulphuric acid. When glucose or sucrose, it is heated with concentrated sulphuric acid, glucose or sucrose, C12H22O11. On heating with concentrated sulphuric acid, that gives sugar charcoal is formed, Or when formic acid, HCOOH, on heating with sulphuric acid, carbon monoxide gas is liberated. This shows sulphuric acid acts as a very good dehydrating agent. Sulphuric acid also acts as a oxidizing agent. It oxidizes Sodium sulfite 2, sodium sulfate, Na2SO3, Na2SO3. On treating with sulfuric acid, H2SO4, that gives sodium sulfate, Na2SO4, Na2SO4. Sulfite is converted into sulfate. Next, about oxo acids of sulfur. Now, first one is about Carose acid, Carose acid. It is also called as permonosulfuric acid. Now, what is the formula of Carose acid? H2SO5. Now, about the structure of H2SO5. There is one peroxy linkage. It's about Carose acid. Now, next about Marshall's acid. Okay. Peroxydisulfuric acid is called as Marshall's acid. Peroxydisulfuric acid, H2S2O8, peroxydisulfuric acid. Now, I'll write the structure like this. Peroxydisulfuric acid is nothing but Marshall's acid. Now, next about the oleum, fuming sulfuric acid, oleum, H2S2O7, oleum, H2S2O7. Write like this. H2S2O7. So these are the important oxyacids of sulfur. Same you can go for sulfurous acid, sulfuric acid. All these are example for oxo acids of sulfur. Now, next, moving on to group number 17. So elements belongs to group number 17. First one is fluorine. Group number 17. Fluorine, chlorine, bromine, iodine, and another one is artificial, prepared halogen. Now, we'll go for the properties. Properties. Down the group, atomic size increases, ionization enthalpy decreases, electronegativity decreases. Now, about the electron gain enthalpy. Chlorine has got more electron gain enthalpy than the fluorine. Then comes bromine and iodine. Now, next about bond energy. Now here you have to consider the molecule of halogen. So chlorine to chlorine is highest. Then comes bromine to bromine. After that, fluorine to fluorine. Next is iodine to iodine. Now, about the stability and oxidizing power. Now, oxidizing power. Fluorine, the highest. Next comes chlorine. Least is iodine. Fluorine, chlorine, bromine, and iodine. Now, about the heat of hydration. Here we consider halide ion. Heat of hydration. Smaller the size of the ion, greater is the hydration effect. So which is smallest ion? F minus, then comes Cl minus, Br minus, then I minus. Okay. So this is about Heat of hydration. Similarly, we will go for reactivity. Reactivity follows the same order. Reactivity. The most reactive is fluorine, then comes chlorine, bromine and iodine. Now, when halogen combines with other element except helium, neon or argon, they form binary halides. They form binary halides. Now, it's about the ionic character of binary halides. Binary halides. First one about the fluoride, chloride, bromide and iodide. So these are binary halides. Now, the first property of binary halides about the ionic character. Ionic character. Say, ionic character decreases as the electronegativity decreases. Ionic character. Decrease in ionic character. Now, about the melting point and the boiling point. Melting point and the boiling point. Melting point and boiling point. So, iodides are having high melting point as well as boiling point. Now, next about reducing character. Reducing character. So, about the reducing character. Reducing character. Now, Psi minus. Then comes Br minus, Cl minus and F minus. This is a decreasing order of reducing character of halides. Now, so percentage of ionic character and thermal stability. Percentage of ionic character. It depends on the electronegativity difference. So, HF is more than the HCl. HCl is more than the HBr and least is HI. Least is HI. Now, and next we will move on to acidic nature. Acidity. Acidic nature. Acidic nature. So, HI is more acidic than the HBr. HBr is more acidic than the HCl. Then least acidic is HF. Least acidic is HF. Now, about the reactivity of chlorine. Reactivity of chlorine. Now, first we will go for preparation of chlorine. When potassium permanganate reacts with HCl, potassium permanganate reacts with HCl, that liberates chlorine. That liberates chlorine. Say, preparation of chlorine. Here potassium permanganate, it acts as a oxidizing agent. Oxidizing agent. Reacts with HCl. Reacts with HCl to give KCl. KCl. Then MnCl2 plus H2O liberating chlorine. Liberating chlorine. So this is about the lab preparation of chlorine. Now, about some of the properties of chlorine. Chlorine acts as an oxidizing agent as well as a chlorinating agent. Now, about bleaching action of chlorine. Bleaching action of chlorine. Now, when chlorine reacts with moisture, first it gives HCl and hypochlorous acid. Then further hypochlorous acid decomposes to give HCl and nascent oxygen. So due to this nascent oxygen, chlorine acts as a good bleaching agent. It acts as a very good bleaching, and bleaching action is permanent. Bleaching action is permanent. Now, okay. Next one about the displacement reaction. Displacement reaction. Now, so about the displacement reaction. Displacement reaction. Chlorine reacts with potassium bromide. Chlorine reacts with potassium bromide. Chlorine is more reactive than the bromide. Therefore, here displacement reaction takes place. That gives KCl and Br2, KCl and Br2. Now, so reaction with sodium hydroxide is very, very important. Reaction with sodium hydroxide. Now, when chlorine reacts with sodium hydroxide in cold condition, that gives sodium chloride NaCl and sodium hypochlorite. When chlorine reacts with hot solution of sodium hydroxide, hot solution, that gives sodium chloride NaCl and sodium chlorate NaClO3. Okay. Yeah. Just remember this product enough. When chlorine reacts with hot and concentrated solution of sodium hydroxide, that gives sodium chloride and sodium chlorate. Similarly, with the cold and dilute solution of sodium hydroxide, that forms sodium chloride and sodium hypochlorite. About addition reaction of chlorine. When chlorine reacts with sulfur dioxide, that gives sulfuryl chloride. When carbon monoxide reacts with chlorine, that gives carbonyl chloride. It is also called as phosgene. So these are the important reactions of chlorine. Now, next part is about interhalogen compound. When two different halogens, they combine, they form interhalogen compounds. So there are different types of interhalogen compound: AX, AX3, AX5 and AX7. Now, example for AX: CLF, BRF, IF, etc. Now, about the AX3, CLF3, BRF3, IF3. Now, same AX5, CLF5, BRF5. This is IF7. These are examples for interhalogen compound. Now, so about the preparation of interhalogen compounds. These interhalogen compounds are more reactive than the halogen because interhalogen compounds, they are polar due to difference in electronegativity. Therefore, they are more reactive than halogens. Now, about the preparation. When chlorine reacts with fluorine, that gives interhalogen compound CLF. Okay. Here temperature is maintained at 473 Kelvin. So by changing the reaction condition, we can prepare different types of interhalogen compounds. Now, some of the terms like pseudohalogens. Now, the compounds like CN twice, then SCN twice. They exhibit similar properties like halogens. Therefore, they are called as pseudohalogens. Now, similar pseudohalides. CN minus, then OCN minus. These compounds exhibit similar properties just like halides. Therefore, they are called as pseudohalides. Okay. Now, next about oxo acids of chlorine, oxo acids of halogen, or we can take it as a oxo acids of chlorine. Now, first one is HClO, then HClO2, HClO3, HClO4. Now, so general name for the first compound, general name halic 1 acid. This is called as halic 3 acid. Oxidation state is 3. Next one is halic 5 acid. Last one is halic 7 acid. Oxidation state is 7. This is general name. Okay. Now, Here chlorine oxidized +1, +3, +5 and +7. Now, so about the structure of the first compound, One OH group. All these compounds are monobasic. Now, next one. Okay. HClO2. Next compound, HClO3. This is a chloro group. Now, next compound, ClOH. Now, HClO4. See. Now, when you consider these oxo acids of chlorine, see, HOCl, okay, or HClO2, HClO3 and HClO4, right, HClO, okay, hypochlorous acid. Then this is called as perchloric acid, okay, perchloric acid. Now, here in the strength, which is more acidic, and that depends on the oxidation state, say. Perchloric acid is more stable. Now, lastly about the group number 18. Now, in this part you have to concentrate on the compounds of xenon and type of hybridization and about the lone pair and the bond pair of electrons. Now, so example for group number 18. First one is helium, neon, argon, krypton and xenon. Atomic size increases down the group. Then ionization enthalpy is very high but decreases down the group. Electron gain enthalpy 0 because no tendency to gain electron. It is completely filled. No tendency to gain electron. Now, it's about the compound of xenon. The first compound of xenon platinum hexafluoride. That reaction is called as Bartlett reaction. When xenon reacts with the platinum hexafluoride, that gives xenon platinum hexafluoride. Xenon reacts with platinum hexafluoride. That gives xenon platinum hexafluoride. See. And what made Bartlett to prepare this compound? While working with platinum and oxygen, he was ended up with the brown colored compound. Since ionization enthalpy of oxygen and fluorine is same, he replaced oxygen by fluorine. Okay. Now, next, other compounds of xenon. Now, okay. Before that, general property of noble gases. So, melting point, boiling point, polarizability and ease of liquefaction increases down the group. Okay. So, this is about the melting point, boiling point as well as the polarizability. Now, about some of the compounds of xenon difluoride, Xenon Tetrafluoride, Xenon hexafluoride. There is no Xenon trifluoride and Xenon pentafluoride because xenon can combine only with even number of fluorine. That during hybridization process that leads to give even number of half-filled hybrid orbitals. Now, about hydrolysis of these xenon fluorides. Now, Xenon tetrafluoride, when it undergo complete hydrolysis, that gives xenon, and other compound is oxide of xenon and hydrogen fluoride liberating oxygen. Similarly, xenon hexafluoride, when it is subjected to hydrolysis that gives oxide of xenon and hydrogen fluoride. Now, about partial hydrolysis. When xenon hexafluoride undergo partial hydrolysis that gives Xenon Oxy compound with fluorine and HF. Similarly, xenon hexafluoride reacts with 2 moles of water that gives xenon dioxygen difluoride and hydrogen fluoride. When xenon compounds reacts with phosphorus pentafluoride, xenon difluoride reacts with phosphorus pentafluoride. It forms a complex compound like this. Xenon, this acquires positive charge, and platinum hexafluoride acquires negative charge. Now, so about the compounds of xenon with fluorine as well as oxygen. Now, first one, xenon difluoride. This is an example for sp3 dehybridization. Geometry is linear. Now, xenon, 2 fluorine atoms, and these hybrid orbitals contain, say, 3 lone pair. There are 3 lone pair and 2 bond pair. The next compound, xenon tetrafluoride. It undergo sp3 dehybridization. Now, geometry is square planar. Now, xenon, actually it is a distorted square planar because of the presence of lone pair of electron. There are how many lone pair? 2 lone pair. And how many bond pair? 4 bond pairs. Now, next one, xenon oxy compound, that is xenon oxide. It is pyramidal in shape. Say. This contains 1 lone pair, pyramidal. Now, one more compound, xenon oxy difluoride. This contains 2 lone pair, T-shape. Next important compounds of xenon, about xenon hexafluoride. It has got distorted octahedral geometry, and about the type of hybridization is sp3d3. There is 6 bond pair and 1 lone pair, because lone pair that changes the geometry of the molecule. Now, next one, xenon tetroxide. See. Okay. Geometry is tetrahedral. And one more compound, xenon oxy tetrafluoride, is an example for sp3d2 hybridization. Xenon, there are 4 fluorines and 1 oxygen. Geometry of xenon oxy tetrafluoride is square pyramidal. So here you have to concentrate on the lone pair and bond. Once you know the structure, then you can easily make out lone pair or bond pair. In this compound, simple compound, xenon tetrafluoride, how many bond pair? 4 bond pair. And how many lone pair? 2 lone pairs. Xenon difluoride, 3 lone pairs and 2 bond pair. 3 lone pairs and 2 bond pair. So this is about P block, group number 15, 16 and 17 and 18.